So, what if I told you that one of the biggest secrets to your computer's speed is actually hiding inside a math problem you probably learned in grade school? Let's dig in and see how a really simple calculation becomes a physical blueprint for some seriously high-speed silicon.
Well, it all comes down to this thing called the multiplication bottleneck. See, in the world of computer processors, multiplication is just expensive. It eats up time and it eats up a ton of hardware. In fact, the performance of a whole complex circuit often hinges on how fast it can do just one single multiplication. So the big question is, how do we make this one operation as fast as humanly possible?
And the answer, surprisingly enough, isn't some brand new exotic algorithm. Nope. Instead, we're going to ground this super complex hardware problem in a concept that should feel, well, pretty familiar. We're going to look at the blueprint hiding in basic math.
Okay, I know what you're thinking. This equation looks a little intimidating, right? It's the formal, proper math for multiplying two binary numbers, x and y. But don't let the symbols freak you out. You really don't need to memorize it. All this formula is doing is describing, in a very precise way, a process you already know by heart. And this right here, this is the core idea of this whole explainer. The physical layout of this circuit, the actual gates and the wires. It's not just some random design. It is a direct, one-to-one physical copy of the steps you take when you multiply two numbers by hand. The math is the blueprint.
And this slide just lays it out perfectly. Remember doing long multiplication back in school? This is exactly the same thing, just with ones and zeros. You multiply, you shift each row to the left, and then you add them all up. That scary formula we just saw, it's just a fancy way of describing this exact spatial layout. The hardware we're about to build is literally a silicon drawing of this problem.
All right, so let's see how this thing actually gets built. We're going to go from the manual process on paper to the physical architecture, piece by piece. We'll walk through how each little step of that algorithm gets its own dedicated piece of hardware. Okay, so this whole translation happens in three main stages. First, we have partial product generation. That's creating the rows of numbers. Second, we have partial product accumulation. That's where we add them all up. And third, the final addition to get our answer. This is our roadmap for the circuit. Okay, phase one, generating the partial products. How do we create each row of our multiplication problem? You're going to love how simple this is. In binary, you're only ever multiplying by a 1 or a 0, right? So each row in our problem is either a perfect copy of the top number or it's just a row of zeros. And you can do that with a dead simple set of logical AND gates. Now, this is where it gets really clever. In the manual process, we shift each new row one spot to the left. So how do you build a physical circuit to do that? You'd think it needs some kind of complex logic, maybe a special shifter component, wouldn't you?
Well, the elegant reality is this. The shift isn't a component at all. It's just wiring. By routing the output of one row diagonally to the input of the next, we get that mathematical shift for free. It costs 0 logic gates. It adds 0 time delay. It's just a beautiful example of how a math concept can translate into a super simple physical structure.
And that brings us to phase two, partial product accumulation. Okay, we've generated all our rows. We've shifted them into position with that clever wiring. Now we have to add them all up. This is the heavy lifting of the whole operation. And as you can probably guess, this is the part that eats up the most physical space on the silicon chip. And to do it, we build this massive grid of simple adder circuits. It's a huge array of components, and they're all dedicated to one task, summing up all those partial products. It's this very grid structure, in fact, that gives the array multiplier its name. If we zoom in a little bit, the addition basically works like a chain reaction. It's called a ripple carry. Each little adder does its bit of math, and then passes any leftover value, that's the carry bit, to the next adder down the line. And this complex, crisscrossing flow of signals, that's what ultimately sets the multiplier's top speed.
So, we've seen all the pieces. We've got the generation, the shifting through wiring, and the big accumulation array. Let's put it all together and take a look at the final blueprint.
And there it is. Just look at that. At the very top, you can literally see that layer of AND gates doing the generation. Below that, all the diagonal wiring is providing that free shift we talked about. And the entire rest of the structure? That's the massive adder array doing all the hard work of summation. All those distinct mathematical steps are compacted into one beautiful, highly efficient rectangle of silicon. So at the end of the day, here's what you have to remember. The circuit isn't just solving the math problem. In a very, very real sense, it is the math problem, just drawn in silicon instead of on a piece of paper. The algorithm and the architecture are basically one and the same.
And that just leaves you with this kind of amazing thought, doesn't it? If a fundamental piece of arithmetic can be so elegantly and directly translated into a physical hardware layout, it really makes you wonder, what other beautiful direct translations from pure mathematics are hiding inside the technology we use every single day?